First of all, thanks to Bill and AI Camp for the opportunity. The topic is fine-tuning LLM for custom data set. That's the main idea of this talk. For this talk, I'm assuming that you're sort of familiar with, say, large language models, natural language processing, and what does it mean to do fine-tuning. Of course, we are going through the theory and practical, but generally aware of the context. So let me begin with the background. Why do we do this fine-tuning? So typically, when you have ready large language models, open source or closed source, say things like GPT, generative pre-trained transformers, or Gemini, Gemma, whichever large language models that you have, they're trained on their data set. Maybe they have scraped the whole world and they have been trained on those data sets. So they can answer generic questions, but they are not able to answer your questions on your data. So data that is not accessible to them. So that's the main problem people are facing. I am an AI consultant also, and everybody wants to have ChatGPT-like or Llama-like power on their data set. Right? That's the wonderful thing that you may want to have, right? But you don't want to share your data. That's the main concern. So without sharing your data, can we build a ChatGPT-like or Llama or Gemma-like model? So this is called as domain adaptation, building a large language model on your own data, or ChatGPT-like interface on your own data. That is the basic problem that we are trying to address. Meaning, a ChatGPT-like interface and answering on your data. So there are multiple ways of doing this. A very popular way is prompt engineering itself. I'm assuming you're all familiar with prompt engineering. So if you want to build, you can do few shots prompting, meaning in the prompt itself, you can embed some text, some data from your domain and let the prompt answer from it, right? That's few shots way of doing things. Another way is called as RAG, Retrieval Augmented Generation. Same thing happens, but happens via engineering. When you give a prompt, you have already indexed your data somewhere in some database, vector database. When a prompt comes, it goes and finds the most matching examples. It brings those examples in the prompt, and looking at those examples, the LLM answers, right? That's RAG. So we saw few shots, RAG. And the third one is, of course, fine-tuning. You take the base model and fine-tune on your data. So there are multiple ways of fine-tuning. That's what we will see today. So my talk, I've divided it into 3 parts. First is introduction to fine-tuning and one specific technique called as PEFT or LoRA. That is the first part. Second part, actually, I'll talk about a library, a framework called Ludwig, which helps us do fine-tuning. It's the implementation part. And third part is doing the whole thing on a custom data set. So 3 parts, some theory, one library, and then the practical code walkthrough. That's the idea. So that at the end of the session, you would have seen one end-to-end use case working, of course, in the PPT. So what is fine-tuning? As I said, the generic large language models are generic, of course. They do not know about your data, your specialization. So they lack specialization. And specialization could be domain specialization like medical, legal, pharma. These are domain-specific specializations. Another way of specializing is you can do it for a task. So classification, summarization, those kinds of fine-tuning are also possible. So definition is process of training pre-existing models. Models have to be there. Some base models have to be there. And then you have to have custom data, right? With these two, you should be able to build a fine-tuned model so that it starts answering from your data. So that's the idea of fine-tuning. An example, sir, of course, there are fine-tuned models available. Some companies have built finance fine-tuned model, healthcare fine-tuned models. Many fine-tuned models are available. And of course, the reason, as I've stated here, base models are very raw, very generic. They don't give very specific results, specific to your domains. So we are doing fine-tuning. There are multiple ways of doing fine-tuning. Just one example I saw, by the way, wherever I've used somebody else's context or pictures, I've put the references at the bottom. So just one example here, a base model. Tell me how to fine tune a model, and you see the answers, completion meaning answers, prompt meaning query, and you see the fine tuned model, how it differs. Of course, this is a little oldish examples. Today things may be a little different, but you can get the idea. So this is why we are doing fine tuning. So why? Basically customization, meaning domain adaptation. Your domain, say medical domain or legal domain, although words may be same, their interpretation is different. Let me take one example. So there is a word called set, ACT set. There are multiple meanings of word ACT set in different domains. In Python, it may mean different, Python programming. In mathematics, it may mean different. In civil engineering, it may mean different. So multiple interpretations of the same word. So if you are building something specific to say healthcare or civil engineering, you'll have to have those documents, those custom data sets with which you will fine tune a generic model. So fine tuning LLMs customizes for the domain specific aspects. That's the main idea. And I'll be touching upon this point in multiple slides later on. Why? Because we need accurate results. If it is very generic, it may give wrong answers, very generic answers, which are not useful. So fine tuning ensures accurate and contextually relevant outputs. That's the main idea. So like in different domains, we can fine tune models. Another thing is some things are made mandatory, data compliance, especially in very critical fields like healthcare, finance, law. You have very strict data regulations. So you have to have answers from these documents only, right? If there are certain needs, certain requirements like that, then generic models may not suffice. So you'll have to build fine-tuned model on specific regulatory data. And of course, it addresses the issue of security and privacy. If you fine-tune the model and keep it in your own premises, own machine, own subscription, then of course nothing has gone out of your boundary. So that the whole model, your inferencing, your deployment, everything can happen within your control. Nothing gets sent to some different LLM websites. So data compliance. Another use case is, so you have limited data. For building a large language models, of course, you need large corpus. Almost like whatever is available on the internet, you have to put it. And of course, large networks, large compute, and lot of money, and millions of dollars. You may not have that. If you have little less data, this is supervised fine tuning. So labeled data. Then what do you do? You cannot build a complete model from scratch. So this is where fine tuning comes in the picture. Because you have base model already ready with some data, of course, not very less data, but reasonably less data, then you can adopt the large language model, base language models using the data. So using your little less data. So this is where fine tuning comes in the picture. So there are multiple ways. Those who have done little classical NLP, little earlier NLP than the current generative AI NLP that we are seeing, natural language processing. There used to be something called as transfer learning, if you remember. You have some base model, then and the network is available in libraries, deep learning libraries like TensorFlow or PyTorch. Then what do? You just change the last layer or add the last layer. So base model is already there, which has learned the language, or in case of images, learn the image idea. And then you do classification layer at the end, or whatever, regression layer at the end, typically classification. So this is how we used to do fine tuning, right? It has been task fine tuned, right? So this is the typical classical fine tuning we used to do. Why it is called as feature extraction? Because the existing earlier layers are supposed to be for feature extraction, isn't it, in neural networks? Only the last layer is doing task related work. All right. Full fine tuning. Of course, we are going to see these different types of fine tuning multiple times during this session. Full fine tuning is, of course, not starting from scratch. You don't start the neural network from random weights, but you start with some ready weights, and then, of course, you fine tune based on the custom data. So this is full fine tuning. But everything changes. I'll show a couple of diagrams later. So we saw last layer fine tuning, full fine tuning. This is one example. I'll wait here for a second so that you understand. So there are multiple ways of doing fine tuning. This is called as instruct fine tuning. I'll show you one example a little later also. So you have pre-trained LLM already ready with you. Then you have some data set, which is say prompt and completion, question answer pairs, many such pairs from your domain. And then it results in fine-tuned LLM. Then it starts answering based on the data that you have given. Yeah, this is the important picture you should remember. There are a couple of places in the presentation which are important where I'll stop. So very roughly, you have a neural network. If you retrain all the parameters, this is full fine-tune. If you can understand, full fine-tune. If you just do the last layer, this is like transfer learning we saw. And the third thing which we are going to see today more elaborately is PEFT. You don't retrain the whole thing. You don't retrain train the last layer, but you take a subset. You build additional small network which you train, which helps do fine tuning. So this part we are going to see today. So again, some summary. Supervised full fine tuning I mentioned. Instruction fine tuning is instruction based fine tuning that we saw. Reinforcement learning is actually fine tuning in the sense, it is in the sense of alignment. We are not going to touch upon that topic, but alignment, because some human ranks the output from the fine tuned model. And of course, we are going to dive deeper into this part, PEFT, or the specific technique called LoRA, low rank adaptation. Hopefully, so far we saw the context, why we are doing fine tuning, some basic three examples, three approaches of fine tuning. And we are going to see PEFT in more detail. So in PEFT, as you remember, we are not going to retrain the whole thing. We are not going to retrain the last layer, but we are going to build another small network. And we are going to train that network, and we'll see how. Okay. So it addresses mainly, because we cannot retrain the whole network, because for retraining the whole network, we'll need a lot of compute, lot of money that we don't have. So we are building a small network. and which will try to mimic the whole fine tuning. So PEFT is also library from Hugging Face. I'll show you code example also. So PEFT is what we are going to see today. Go little. There are multiple ways of doing PEFT. We are going to see this portion, not selective, not additive, but reparameterization, a technique called LoRA. Low rank adaptation is what we are going to see today in more detail. And that is the first part of the presentation. Next part will be Ludwig, the framework, and the last part will be actual use case. So we are going to see LoRA now. Okay. So this is again PEFT, parameter efficient fine tuning. What it does, if you have a weight matrix, I'm assuming everybody is familiar. Neural network is nothing but actually bunch of weight matrices, right? And in the back propagation, they get trained so that they settle and start answering or doing the required, start giving required answers. So this is normal. And we can do fine tuning of any weight matrix, but we'll take one example here. So if you have a weight matrix, another weight matrix is put. I'll show you in the diagram also. That is called as LoRA adapter. Okay. You're going to train the LoRA adapter. And then while inferencing, you use both of them together. We'll see how. So we are not going to retrain the whole original matrix that comes with the base model, but an adapter, an additional weight matrix. That's the idea behind LoRA. So the training cost is less. All right. So this is the example. Why LoRA? Because we want to have less computational cost and we have small data also, right? So that's the idea. LoRA aims to reduce computational cost. We'll see one example, more elaborate example, so that everything will be very clear. LoRA is one of the PEF techniques, as we saw. And there are multiple techniques available. Okay, so this is an important slide again. Okay. So typically, say you have a weight matrix, n by n. So there will be n into n parameters or weights to be trained, right? Everybody okay with this? So we use this matrix multiplication trick, if you remember. If there are two matrices, m into n, then we can split them m into r and r into n, if you remember. If these two matrices multiply, that also results into m into n. So the middle portion gets sort of cancelled, not cancelled, but two matrices when multiplied like that, m into r, r into n, then it becomes m into n. Hopefully everybody remembers that this is the matrix dimension rule. So this rule is used. So instead of n into n, which is the original matrix, we build another matrix, but not fully, but we split it into two matrices, n into r and r into n. So what happens with this? Instead of training n into n parameters, which is a huge number, we do these many parameters plus these many parameters. So it becomes an addition. So this plus this, only this much parameters we have to train. I'll wait here till everybody gets this idea, because this is the most important concept in LoRA. And what is R? R is actually rank. If you remember, if you have done linear algebra, if you are solving simultaneous equations, right? We represent simultaneous equations, the coefficient matrix, and then the x1, x2, x3, and the finally results, right? That's how we solve simultaneous equation. And if you remember, if two of these equations are dependent on each other, meaning they are convertible to each other, one of the equation is not needed, that is redundant. So only remaining independent rows are what we are looking for, right? If you remember the simultaneous equation theory. So that number of independent variables actually are the rank of the matrix, if you remember. So we are leveraging rank of the matrix. So R is rank. So instead of doing n into n, we split it into two matrices, n into R into n. And then we can use this. And finally, of course, we make it n into n and then use it for inferencing. So this is the basic concept behind R, rank and then LoRA. So why we are doing this? Again, going back, if you have base model, as we can see here, pre-trained weights already ready with us, base model, Llama 2 or whatever, Gemma, Gemini, whichever, typically open source because weights have to be available to us. Then this is the additional delta weight matrix. Let's call it delta weight matrix. Combined W and delta W, we are getting the fine-tuned model. Why? This is the base weights. These are the weights for our data set. So this is an additional weight which helps us fine-tune the original one to answer from us, right? This is another set. We are adding on top of it base model plus healthcare weights. That becomes healthcare fine-tuned model. Base model plus legal model weights. That becomes legal fine-tuned model. Hopefully, you are getting what I'm trying to see. So we are basically trying to come up with such deltas so that once they are added to the base model, it starts acting like healthcare model or a finance model. So that's the idea behind LoRA. All right. So this is what we do. What is this delta matrix? This is nothing but, as we saw, we can split it into a column-like or a row-like matrices, and then multiplication will result in this. So we want this, but we don't compute it. We train only the row and the column matrices, and R is the parameter. Typically, R we can decide almost like a hyperparameter tuning. So we can try R, and R is chosen. All right, this is an important slide. I'm assuming that you will be able to see, but anyway, I will read through it. So this is like a transformer architecture or a feed-forward neural network architecture. So we add LoRa adapter. So this is the base model, if everybody can see my cursor. And what is this base model? It has been expanded here, if you can understand. So X here comes to the original base weights, gives some output. Same X goes through our LoRa adapter. Everybody, I'm assuming that you are getting what I'm saying, and which is internally two, a row matrix and a column matrix, isn't it? It also generates. Finally, this output and this output are combined to make the prediction. From X, we predict Y. I'm assuming everybody is familiar with deep learning. And then that is compared to the actual Y. This is supervised. Whatever the difference is, that is the loss. We have loss formulation also. That loss formulation goes back in back propagation and adjusts only the LoRa weights, only the adapter weights. I'm waiting here till everybody gets it. The original base model weights are not touched. They are frozen. You can see we are training only small number of weights. So that's the idea behind LoRa. If you get this mechanism, you have got it. So that's the main idea behind LoRa. All right. There is a little bit details, but I think you have got the idea. Of course, if you have questions, I'll take them at the end of the session. So this is one sample, LoRa code. Of course, this is like academic sample. With Hugging Face Transformers library, you get this. Hugging Face, as I said, PEFT library is also available with them. You get the base model here. You can put more or less whatever is available on Hugging Face as the base model, whichever allows this. And then you do LoRa config. The most important parameter, as you know, is R rank and few other parameters. That's about it. You train it, get the model, and you can see the number of parameters less than the original. This is about whatever 0.16%. So with the small adapter, when put on top of the base model, you have got the fine-tuned model. A wonderful part is Same base model, but you can have multiple adapters. One finance adapter, one legal adapter. Within legal also version 1, version 2. So such way you can build your LLM ops also. So this is Hugging Face sample of fine-tuning LoRa. Next, in the second part of the presentation, I'm going to talk about Ludwig way of doing fine-tuning. We have this 38 minutes already done. I'll quickly go through. All right. There are other types of LoRa, also quantized LoRa and other parts. Yeah. So basically, LoRa is best technique for fine tuning, and it is computationally light because we train less number of parameters. All right. So that's about LoRa. All right. So now that we have understood basic fine tuning and little bit about LoRa, now we will talk about. We have also seen one example of Hugging Face way of doing LoRa fine tuning. We'll see Ludwig way of doing fine tuning, and you'll see the marked difference. Okay, how LoRa fine tuning can be done very quickly, very efficiently using Ludwig library. What is the idea behind Ludwig library? By the way, Ludwig is by a company called Predibase, and this is the open source library that they have put. The original idea is by a co-founder, Piero, when he was working on machine learning models, and this is experienced by most of the machine learning guys. You build some, say, intent classifier, 1,500 lines, while developing, then many steps are there. You do iterations. Finally, till deployment, it will take 5 months, 7 months, right? Till you get everything right. Similarly, fraud prediction, will take 5 months till deployment for production ready deployment. So many people, basically, such ML models development and deployment would take weeks and months, isn't it? And if you can imagine, most of the code is actually boilerplate, meaning sort of same. Only a few things we change and see the effect. Again, change few things is more of an experimentation, isn't it? That's what we do as a machine learning engineer. Many experimentation till we get the things right. So this is what Piero, this co-founder, you can see the picture, observed, and then they came up with one idea, which is, why don't we just do a config-like thing, YML, only few parameters, and rest of the code is automatically done in the background, and only these parameters you change and rerun, right? So while writing the configuration file, it won't take a lot of time. Of course, you have to be knowledgeable about which parameters to choose. I'll show you some examples, okay? That's the idea behind Ludwig. Rather than writing code, write only the configuration file, config YML, and then keep on experimenting only using the config file. Isn't it? Won't that be wonderful? That's the idea. Okay. Some examples here. If you're building, you can easily read the config file and guess what it would be doing. So input features, sentence type text, meaning I can see that it's almost like a sentiment classifier like model. And output is intent category, a multi-class classifier, right? Simple. Just mention these, and with some code, you can run this config and done. That's about it. Little more expert level control. Apart from this, if you want a specific encoder, because sentences you cannot put into machine learning directly, you have to vectorize them, you have to word embed them or doc embed them, right? And there are encoders, many encoders are available. BERT is one of them. Just specify you want BERT here and some training parameters. That's little more control than this. If you want more control than this, of course, those are possible. That is also possible. Hyperparameter tuning, hyperparameter optimization, you give the ranges. So such levels of expert controls are also available. If you don't want anything of this, just this much is enough, isn't it? Some things are defaulted, meaning automatically chosen for you. That's the idea behind Ludwig. We'll see directly one example of LoRA. Of course, some information uh, about Ludwig. So just pip install Ludwig and then get going. This is open source. It can do multiple things it can do machine learning also, deep learning also, and of course, LLM fine tune also. Okay, that's the idea. I'll rush a bit, just 17 minutes left, I think. I'll show, you can do regression, text classification, image, many classical ML or NLP related things also you can do using Ludwig, but I'll show you LoRA example today. All right. Many things like this. Okay. Yeah. For LoRA, what do we have to say? Adapter type is LoRA, R is this, something like this. And that's about it. You mention this paragraph in config file, and that's it. Of course, we'll see one full-fledged example later, but this is as simple as it gets. Not even like what we did for Hugging Face library. At least there you had to write what 10, 20 lines, right? Here just 4, 5 lines and you are good to go. That's the power behind Ludwig library. So I'm going to show you a full example. Of course, this is sample example. Base model, LoRA. This is instruct fine tuning. If you are familiar with this, you have to put prompt instruction and give question and answers or input and input, output, some fine tuning parameters, and that's about it. Once this config is ready, you build a model. You have data sets of input and output columns, text columns. That's it. Model is trained. It is as simple as this using Ludwig library. I'm going to show you full-fledged example in the third part of this talk. That's about it. So we are going to now see the actual full-fledged example of fine-tuning Gemma, Google's open source model using a custom data set. And this custom data set is called GST. This is basically a goods and services tax, which is used in India. And this is GST FAQs, question answer, input output. So once such data set is available, using that data set, I'm going to fine tune Gemma. That's the idea behind next few slides. Okay. Gemma, as you know, some information by Google. Ludwig is the library we are going to use. Goal is to do fine tuning using LoRA. I'm mostly going to show you the config file and then we are good to go. This is some sample. By the way, I have a blog. I'll quickly show you here. Gemma for GST, which talks about, this is on Medium. Gemma, if you search by name, Gemma for GST, my name, and then on Medium, you will see step-by-step explanation, almost like a Python or Jupyter notebook. Okay. But I'll quickly walk you through here itself. You have to do some installations. Of course, you have to have access to Hugging Face because Gemma is coming from Hugging Face. And you have to have data set. Okay, I've given links to the actual path in my blog. You can take them. So this is nothing but question answering data set. You can have your own data set and fine tune Gemma or any open source large language model using this methodology or approach. All right. So how do we specify? You must be familiar by now. Base model, Gemma. You are doing QLoRA quantization. LoRA is the adapter type. Then you do instruction. And this is instruction fine tuning, meaning prompt based fine tuning. Input features question text type. Output features question. So this is question answer pair, right? This is the data set. That's about it. With this, you should be able to, and then some of those fine tuning parameters. And then you do Ludwig model and then start doing inferencing. All right. How do you do that? This configuration that we saw, put it in the Ludwig model constructor, get the fine tuning and do training on the data set. The CSV data set that you have, read it as a pandas data frame, put it as a DF. That's it. Instruction fine tuned model is ready with you. How to use it? I'll show you with one example. Similarly, have testing DF and infer it. Right? If you have testing DF like this, predict. That's about it. The answers will come. It is as easy as it looks. Okay. And if you want to have expert level controls, of course, you can have expert level controls in the configuration file itself. So this is what I wanted to cover: introduction to fine tuning, Ludwig, an actual one example, end-to-end example. So now I think we have still 10 more minutes to go. If at all you want to connect with me, this is my LinkedIn. By the way, you can just follow me. My connections are full, so just follow me there. I'll request Abhi to read questions, and I'll try to answer them. Hello. Are you able to hear me, Bill?
Yes. Sorry. Sorry about it.
I'll take up questions now, whatever are there in the chat window. Maybe if I can see. Oh, I cannot.
Okay. Yeah, you if you can scroll up a
Let
little
me just,
bit. I
yeah,
see
okay. I
a
think
few
this
questions.
is
Yeah, thanks a lot for the presentations. And we are come to the Q&A. If you have any questions, please post in the room chat. We will go through them. If you prefer to ask questions, feel free to raise your hand. We can unmute you and you can speak to ask questions. Please go ahead if you see some questions you want to answer.
okay. People are asking. The questions here. Yeah. I'll be sharing the PPT. Let me just quickly show you my GitHub. And things are okay. This is my GitHub, very simple, Yogesh HK. Multiple repositories. There is a repository called Teaching Data Science. Maybe I'll show you that as well. There you see contents of this presentation.
Yes, so
there are later.
later you can send me those GitHub link and PowerPoint. We will share to all of our attendees.
Yeah. So Bill, I have emailed you that. If at all you want to share it in whichever drive way or wherever, you feel free to share it.
Yep, yep.
Yeah. So how can we save model? Yes, Ludwig model, the fine-tuned model can be saved. Just look at some examples on the website. By the way, I'll just quickly show you Ludwig's GitHub repo also. You can find it, Ludwig by Predibase. They'll show you all the tutorials and documentation. Let me, I think people are asking to put link in the chat window itself.
Yes, Yogesh. People are asking to put your LinkedIn
Medium
and
blog here.
Medium blogs.
Yeah,
Yeah.
I'll put it here. Okay. And I'll show you my LinkedIn. Hopefully people can see that. Okay.
So Nancy has put
Okay,
the question, what kind of programming languages would you recommend?
So I'm very biased towards Python. I use Python, but of course people use other languages like R, Java, C++. But if I have to suggest you, that's Python. Use cases for LoRA, of course, multiple use cases. One of them is this fine tuning. Basically, you can have your any data set in insect question answer format from medical, legal, finance, any domain, and then you can use LoRA to do fine tuning. Okay. Any other question that you are seeing?
Link,
How to select LoRA parameters? Of course, you start with the standard ones, but of course, it comes with the expertise.
On GCP, is there any advantage?
Okay.
So is
The
there
LoRa
any
hyperparameters.
advantage to use LoRA today?
Yes, of course, as I said, you don't have to fine tune the whole model, meaning all the weights, but with less number of weights, you can get similar effect. Yes, I think you will get the slide deck. By the way, it is not PPT PowerPoint. This is made using LaTeX. So it's a PDF, a slide deck, which I have shared with Bill, and Bill will share it with you later.
So the next question is there strategy to noise device before
Maybe you are not
potentially
audible to me.
local minima?
Bill, am I the
Yeah, I
audible?
think the maybe your network is
there
kind
any
of
strategy?
delay. Let us see. So
I
Yogesh,
can-
probably you can just read the questions by yourself.
Yes,
and,
I can read it myself. Yeah, I think. Let me just quickly go. Is LoRa better than randomly choosing a subset? Obviously, by the way, as you can yourself understand, if you have original n by n matrix, if you randomly choose, then that's the original model itself. By LoRa, what you are doing is you are mimicking the fine-tuned model, right? This second part is trained on your custom data set. If you just randomly pick from the base model, it will still answer from the base model. So that's not the purpose. Purpose is to do fine-tuning. What kind of projects would you encourage the use of? As I said, if you have custom data and if you want to build a fine-tuned model, that's, by the way, I'll mention a progression. Okay. We saw 3 ways of doing domain adaptation. First is few shots. Second one is RAG, retrieval augmented generation. And the third one is fine-tuning. We saw fine-tuning today. Based on the expertise and money that you have, you can choose either of them. I mean, this is a progression. If you just have small examples, few shots learning, not much money is needed. You just have to put that context in the prompt and start using it. If you have little more data and little more money and engineering expertise, then you build RAG, retrieval augmented generation. And if you have more money, more expertise, and more data, you do fine-tuning. So this is the progression. But of course, the results are also in the progression. In fine-tuning, you'll get far better results than the few shots prompt, right? That's obvious. How much does this cost affects? Actually, of course, it is hard to estimate anything. It depends on the infrastructure that you're using, which cloud provider you're using, how much data that you have. This is all is obviously cannot estimate just like that. Okay, so where to train the data? Of course, based on if you have terabytes of data, you cannot do it on laptop. If you have large base model itself, you can do it. You cannot do it on laptop. So there are hosted services to do this, and of course, many of these cloud providers would be more than happy to do this fine tuning if you have large data, large compute to be done. Maybe I'll take just one or two more questions.
Yeah, we can wind up the session as time is going to over 8:58.
Is fine. Maybe this is the last question. Like, is fine tuning accurate? I think the basic guess is, of course, fine tuning would be more accurate because the weights themselves have been trained. RAG is based on similarity. If you know, a prompt is vectorized. That vectorized prompt goes to vector database. Match is done, and the answers are brought to the prompt, and the answer is this is fine tuning is far more sophisticated than this. So maybe if at all you have questions, you can send email to me. I've given my email address. I'll write it here as well. Actually, when I pasted, it went to somebody else. Maybe. Okay, meeting group chat. I'll share the links again. I think this is for everybody. I'm assuming that you will get it here. Okay. I think this is what everybody will see now.
Yes, Yogesh, we
And
can able to see your
yeah,
meeting.
and my email is if at all you have questions, you can email me. It's my full name, Yogesh Kulkarni at yahoo.com. Once again, thanks AI Cam, Bill and Abby for the opportunity.
Yeah. Thank you all for joining us today. Your participation what makes this session great, and